All right, welcome to the Explainer. Today we're going to talk about the three little engines that pretty much run our entire digital world: the CPU, the GPU, and the TPU. And look, we're basing this explainer on a great report from Virtualization Options LLC, which was really designed to help leaders, folks who aren't necessarily deep in the weeds tech experts, get a real handle on this stuff.
So here's how we're going to break it down. First up, we'll do a quick primer on why we even have all these different chips. Then we'll dive into the CPU, the versatile brain. After that, the GPU, the parallel powerhouse. Then we'll hit the TPU, the AI specialist. And finally, we'll bring it all home and talk about how to pick the right tool for the job.
And you know, that really leads to the biggest question of all: why? If these chips are all so powerful, why do we need three different kinds? Why can't one super chip just do it all?
Well, the answer to that question comes down to one simple word: specialization. As what we ask our computers to do has gotten way more complex, our processors have had to get specialized right along with them.
Think about it. Back in the day, computers did pretty simple stuff, so one type of processor could handle it all. But that one-size-fits-all approach, it just couldn't keep up when we started demanding things like incredible graphics and, more recently, complex AI. The general-purpose chip became a bottleneck. So, the solution was to start designing chips for very specific jobs, trading a little bit of flexibility for a massive, massive boost in performance.
All right, so let's kick things off with the OG, the original all-purpose solution, the CPU. The absolute best way to think about it is as the conscious, decision-making brain of any computer. The central processing unit, or CPU as we all know it, is really the cornerstone of all computing. It's a master of all trades. It's designed to handle the millions of different, varied instructions it takes to run your operating system, your web browser, your business software. It's the thing that's actually making sure everything plays nice together.
So, what's the CPU's superpower? It's pure versatility. I love this analogy. Think of it like a master chef, a Michelin star chef who can cook any dish you ask for, one at a time, but with incredible speed and precision. That's what we mean by low latency. You click a button and boom, something happens instantly. It's a genius at juggling lots of different tasks and making complex logical decisions.
But here's the catch with our master chef. If you suddenly ask that one chef to chop 10,000 onions all at the same time, they just freeze. They can't do it. And that right there is the CPU's big limitation. It's just not built for thousands of simple, repetitive tasks done all at once. And guess what? That's exactly the kind of work that modern AI demands. This created a huge problem, a bottleneck, that paved the way for something new.
And that something new brings us right to the GPU. The parallel powerhouse. This thing didn't just solve the CPU's problem. It completely changed the game for high-performance computing, especially for AI. So, the GPU, or Graphics Processing Unit, was actually born to do something else entirely: make video games look amazing. But here's the cool part. Remember our master chef analogy for the CPU? Well, a GPU is like having an army of 10,000 kitchen assistants. Each one has just one tool. Say a knife. They can't cook you a gourmet meal, but they can all chop an onion at the exact same moment. It was a happy accident, really. Researchers figured out that this architecture, thousands of simple little workers all doing the same thing at once, was perfect for the math behind AI. Just let that number sink in for a second. I mean, a really good CPU might have, 16, maybe 32 cores? A modern GPU? We're talking over 16,000. That is not a small difference. It's the difference between a small team and an entire army. And that's where its incredible power comes from.
So this army of cores is what gives the GPU its superpowers. First, that massive parallelism is just unmatched. It's also fantastic at the specific kind of math with decimals, called floating point, that AI relies on. And to keep that whole army busy, it has a massive pipeline for data to flow through. And that's why the GPU basically became the undisputed heavyweight champion, the engine that powered the entire AI revolution.
You know, it's not an exaggeration to say that the whole AI boom we're living through, it was kicked off by the GPU. The real aha moment came in 2012. An AI model called AlexNet, running on GPUs, just absolutely demolished the competition in a huge image recognition contest. That single event basically proved to the world that this deep learning thing was for real. After that, things just took off.
But you know how it is. Ambitions get bigger. And as companies like Google started thinking about AI at a global scale, even the mighty GPUs started to show some strain. They didn't just need more raw power, they needed more efficiency, more bang for their buck, or more accurately, bang for their watt. And this need for ultimate efficiency led to the next step in the evolution, the TPU.
Okay, so this is the key difference. Unlike the GPU, which was kind of this happy accident for AI, the TPU, or Tensor Processing Unit, was designed from day one with one job and one job only, to crush machine learning tasks. It's what's called an ASIC, an application-specific integrated circuit. Fancy term, but it just means it's a chip that's been stripped of everything it doesn't need to be ridiculously good at just one thing. And you don't have to take my word for it. This quote from Norman Juppy, one of the lead engineers at Google, just nails it. So you hear that? The goal wasn't just faster. It was an order of magnitude. That's 10 times the performance for every watt of power used. When you're running things at Google scale, that's not just a nice to have. That's about saving a fortune on electricity and not having to build a dozen new power plants just to run your AI. So its strengths are, as you'd expect, laser-focused on that one job. It's designed to do one type of math, matrix calculations, incredibly fast. And that just happens to be the native language of AI models. It delivers unbeatable energy efficiency and predictable, consistent performance. So for any business running AI around the clock, that efficiency, that's not just some technical detail. That translates directly into huge savings on your operational costs. It's a massive competitive edge.
But there's always a trade-off, right? When you specialize this much, you give up flexibility. It can't run your operating system or your favorite video game. It's mainly built for Google's own AI tools, and it's not something you can just go out and buy off the shelf. You access it through Google's cloud. So it's an incredibly powerful tool, but for a very specific set of jobs, in a very specific environment.
Okay, so let's pull all these threads together. The big takeaway here is that it's not about one chip being better than the others. It's not a competition where one replaces the other. Modern computing, especially for AI, is a team sport. It's about using all three of these processors for what they do best.
A really helpful way to visualize this is as a spectrum. On one end, you've got the super flexible do-anything CPU. Move along a bit, and you get the GPU, which is specialized for doing many things at once. And all the way at the other end, you have the hyper-specialized TPU, built for pure AI efficiency. And the key concept is this. As you move along that spectrum, you're trading that do-anything flexibility for huge, massive gains in performance and efficiency on one specific task.
This table really lays it all out, side by side. Just look at the difference in core count and clock speed. The CPU, a handful of lightning-fast cores for complex one-off jobs. The GPU, thousands of slower cores for massive parallel jobs. And the TPU, it basically says, I don't even need traditional cores, and uses a specialized hardware block just for AI math. Each design is perfectly sculpted for its primary function.
But honestly, for any executive or leader thinking about budgets and strategy, this chart right here, this is the money shot. This is performance per watt. It's how much AI horsepower you get for every dollar you spend on your electricity bill. And you can see, for big AI jobs, the TPU isn't just a little more efficient. It's in a completely different league. That gap you see, for a large company, that can mean millions of dollars in savings every single year.
So, at the end of the day, the question isn't which chip is best. The question is, which chip is right for the job I need to do? You need your flexible CPU to run the day-to-day business, but you bring in the specialized power of GPUs or TPUs to do the really heavy lifting for AI and data analysis. Understanding that is everything when it comes to making smart tech investments.
And that really brings us to the final and most important question, the one for you to think about. We are now firmly in an era of specialized computing. AI is becoming a part of literally every industry. So the question for you and your organization is, how are you going to mix and match these powerful, specialized tools to solve your unique challenges and build a real, lasting competitive advantage?